Hello there, and welcome to the Scientist Sleepy. Have you ever paused, truly paused, to consider the sheer, staggering immensity of everything? From the invisible dance of the smallest particles to the colossal sweep of galaxies across the cosmic stage, how does this vast, intricate tapestry of existence truly measure up? Tonight, we embark on a gentle exploration into the incredible scale of the universe, from the tiniest quarks to the grandest galactic structures. As we settle in, perhaps take a moment to find your most comfortable position. Let your shoulders soften, your breathing deepen. If it feels right for you, gently press that like button so that more seekers of quiet wonder can find this peaceful haven. And consider subscribing so you don't miss our future journeys into the calming mysteries of the cosmos. If you feel moved to share, I invite you to leave a comment below. Tell me, what aspect of this vast universe sparks the most wonder in you? Your thoughts, like distant starlight, can illuminate our shared journey. Now, let us begin our journey into the profound scale of existence. The universe's tiny secrets are vastly larger than we imagine. Beneath the surface of our everyday reality, in realms far too small for our senses to perceive, lies a universe of astonishing complexity and profound significance. We often think of the grand cosmic structures, the swirling nebulae, the distant galaxies, as the epitome of the universe's scale and wonder. Yet the very foundations of existence, the fundamental building blocks of all matter and energy, operate on principles that are not only counterintuitive, but also possess an influence that ripples outwards, shaping the very fabric of the cosmos. When we speak of the universe's scale, we are not just talking about immense distances and vast expanses of space. We are also referring to the incredible depth and intricacy found within the smallest constituents of reality. These tiny secrets, these fundamental particles and forces, are not merely minuscule components. They are the architects of the universe, the silent sculptors of all that we observe and all that we are. The quantum realm, where these secrets reside, operates under a set of rules that challenge our macroscopic understanding. Yet it is within this microscopic domain that the grandest cosmic narratives are written. The energy, the interactions, the very potential for existence that resides within these subatomic particles and fields is a testament to a scale of influence that far transcends their diminutive size. It is a reminder that true immensity can be found not only in the outward spread of the cosmos, but also in the inward depths of its fundamental constituents. The secrets held within the atom, within the quarks and leptons, within the very fields that permeate spacetime, are not just secrets of matter. They are secrets of the universe itself, secrets whose implications are as vast and as far-reaching as the most distant star. Our exploration into these minuscule realms reveals a universe that is, in its most fundamental aspects, far grander and more awe-inspiring than we could ever initially conceive. The sheer density of information, of potential, and of interconnectedness within these tiny entities is a testament to a cosmic order that is as profound in its minuteness as it is in its immensity. It is in these hidden, microscopic universes that the grandest cosmic truths are often found, whispering their influence across the vastness of space-time, shaping the very nature of reality from the smallest conceivable scale to the most expansive cosmic structures. The universe, in its infinite wisdom, has woven its most profound mysteries into the very smallest of its components, and by understanding these tiny secrets, we begin to grasp the true, immeasurable vastness of existence. These fundamental particles, though infinitesimally small, are the seeds from which all cosmic phenomena sprout, and their inherent properties dictate the grand unfolding of the universe. The universe's tiny secrets are vastly larger than we imagine. The smallest constituents of reality, the fundamental particles and the fields that govern their interactions, hold within them a power and an influence that far exceeds their minuscule size. This is not a universe built from inert building blocks, but one alive with dynamic, interconnected forces operating at scales that elude our direct perception. When we delve into the realm of quantum mechanics, we encounter phenomena that defy our everyday logic. Yet these are the very mechanisms that underpin the stability of atoms, the fusion within stars, and the very existence of matter itself. The energy contained within these fundamental entities, the intricate dance of their interactions, and the pervasive nature of the fields they inhabit suggest a scale of influence that is truly cosmic. Consider, for instance, the concept of quantum entanglement, where particles can become linked in such a way that they instantaneously influence each other, regardless of the distance separating them. This interconnectedness, operating at the most basic level of reality, hints at a universe that is far more unified and profoundly linked than our macroscopic perspective might suggest. The implications of this are staggering. What happens in the smallest, most hidden corners of existence can have repercussions that resonate across vast cosmic distances. Furthermore, the concept of quantum fields, which permeate all of space-time, suggests that even seemingly empty space is not truly empty, but is a vibrant medium teeming with potential. These fields are the true substance of the universe, and the particles we perceive are merely excitations within these fields. The energy density of these quantum fields, though a subject of ongoing research and theoretical debate, is thought to be immense, far greater than the energy contained within all the matter in the observable universe. This vast, underlying energy suggests a cosmic reserve of potential that dwarfs our current understanding. The universe's tiny secrets are not merely about the size of its constituents, but about the immense power and interconnectedness that resides within them. The influence of these fundamental elements extends far beyond their physical dimensions, shaping the very laws of physics and the grand cosmic evolution. It is a paradigm shift in our understanding of scale, moving from a purely spatial conception to one that embraces the profound influence of the infinitesimally small. The universe, in its most fundamental makeup, is a testament to this principle, that true immensity can be found not only in the outward reach of galaxies, but also in the inward depth of its most basic components. These minuscule entities are the originators of cosmic phenomena, and their inherent properties dictate the grand unfolding of the universe, a universe whose most profound truths are often found in its most hidden, microscopic aspects. The scale of their influence is not measured in meters or light years, but in the fundamental shaping of reality itself. The universe's smallest secrets are indeed its largest truths. Even the smallest particles possess an influence that resonates through the entirety of existence, shaping the very fabric of reality in ways that defy our everyday perceptions. When we think of influence, we often imagine grand gestures, colossal forces, or the actions of large, tangible entities. Yet in the realm of the quantum, the infinitesimally small wield a power that is both profound and pervasive. Consider, for a moment, the electron. This fundamental constituent of atoms, with its minuscule mass and charge, is the bedrock upon which all chemistry is built. Its behavior, governed by the enigmatic laws of quantum mechanics, dictates how atoms bond, how molecules form, and consequently, how the entire material universe takes shape. The specific arrangement and interactions of electrons around an atomic nucleus determine an element's properties, whether it will be a noble gas, inert and aloof, or a highly reactive alkali metal eager to share its electrons. This dance of electrons is responsible for the strength of the bonds in the steel of a bridge, the intricate folding of a protein that allows life to flourish, and the very light that allows us to perceive our surroundings. The electromagnetic force, mediated by photons, which are massless particles of light, is another example of this principle. This force governs everything from the attraction between a magnet and a piece of iron to the complex signaling pathways within our own nervous systems. Without the precise interactions dictated by these fundamental forces and the particles that mediate them, the universe as we know it would simply not exist. Even the seemingly empty space around us is not truly empty. It is a dynamic arena filled with these fundamental particles and their interactions. The quantum vacuum, far from being a void, is a sea of fluctuating energy where virtual particles flicker in and out of existence, a constant, subtle churning that underpins the stability of all matter. The very act of observation at the quantum level can alter the state of a particle, a phenomenon known as the observer effect, demonstrating that even our passive presence can have an impact. This interconnectedness, where the smallest components exert such far-reaching effects, suggests a universe where everything is intricately linked, a grand tapestry woven from the threads of fundamental particles and their ceaseless interactions. It is a reminder that the grandest structures are built upon the most humble foundations, and that even the faintest whisper in the quantum realm can echo through the cosmos. The subtle hum of the smallest particles orchestrates the grand symphony of existence, proving that true power often lies in the quietest, most fundamental of places. Quantum fields are the true fabric of reality. Imagine, if you will, a reality not made of solid little particles bumping into one another, but rather of something far more fundamental, more pervasive, and ultimately more elegant: quantum fields. For centuries, we've conceived of the universe as being built from discrete, tangible building blocks, atoms, then subatomic particles like electrons and quarks. This intuitive picture, while incredibly useful for understanding much of the macroscopic world, begins to fray at the edges when we delve into the deepest mysteries of existence. At the quantum level, the very notion of a persistent, localized particle dissolves, replaced by the concept of a field that permeates all of space and time. These quantum fields are not like the fields we might imagine in everyday life, such as a magnetic field or a gravitational field, which are forces acting asterisk upon asterisk things. Instead, quantum fields are the things. They are the fundamental entities, the underlying substratum of all that exists. Think of it this way. A particle, like an electron, isn't a tiny, hard ball. Instead, it's a localized excitation, a ripple or a vibration within a pervasive electron field. This electron field exists everywhere, in every point of space, and it is only when this field is excited in a particular way that we perceive it as an electron. Similarly, quarks are excitations of the quark field, photons are excitations of the electromagnetic field, and so on for every fundamental particle we know. These fields are not static, they are dynamic, constantly interacting, fluctuating, and exchanging energy. The vacuum, that seemingly empty space we often envision, is not truly empty at all. It is a sea of these quantum fields, teeming with potential. At the lowest energy state, These fields are not zero. They possess a fundamental energy, a quantum hum. And it is from these energetic fluctuations that particles can momentarily pop into existence, only to vanish again, obeying the peculiar rules of quantum mechanics. This paradigm shift from particles to fields is one of the most profound revolutions in our understanding of the universe. It suggests that the universe is not a collection of separate objects, but rather a unified, interconnected whole, where everything arises from the same fundamental substratum. The interactions between these fields are what give rise to the forces we observe, the particles we detect, and ultimately, the very structure of the cosmos. It's a view that imbues even the seemingly empty void with an astonishing richness and complexity, revealing a universe far more dynamic and interwoven than our senses might initially suggest. And in this vast, interconnected tapestry, every vibration, every tremor within the quantum fields contributes to the symphony of existence. The Higgs field gives everything its mass, a cosmic sculptor. Imagine, if you will, a vast, invisible ocean that permeates every nook and cranny of the universe. This isn't an ocean of water, but an ocean of energy, a fundamental field that underlies all of reality. This is the Higgs field, and it is perhaps one of the most profound and elegantly simple concepts in modern physics, yet its implications are anything but simple. It's the reason why particles have mass, why they aren't just massless wisps zipping through space at the speed of light. Without the Higgs field, the universe as we know it simply wouldn't exist. Atoms wouldn't form, stars wouldn't ignite, planets wouldn't coalesce, and life, in any form we can comprehend, would be impossible. The Higgs field acts like a cosmic molasses, a subtle resistance that certain fundamental particles encounter as they move through it. The more a particle interacts with this field, the more it drags, and the greater its mass appears to be. Think of it like walking through water. Some things, like a tiny pebble, are barely affected, while a large boulder will feel a significant resistance. The Higgs field works in a similar, albeit far more fundamental, way. The concept of the Higgs field arose from the need to reconcile the standard model of particle physics with the observed reality of mass. Early theories predicted that fundamental particles, like electrons and quarks, should be massless. This was a significant problem, as we clearly observe that these particles do indeed possess mass. The Higgs mechanism, proposed by Peter Higgs and others in the 1960s, provided a theoretical solution. It posited the existence of this omnipresent field and a corresponding particle, the Higgs boson, which is an excitation, or a ripple, within the field. The discovery of the Higgs boson at the Large Hadron Collider in 2012 was a monumental achievement, a triumphant validation of this elegant theoretical framework. The Higgs field is not something we can directly see or touch. It's an abstract but very real component of the quantum vacuum. It is always present, even in the deepest reaches of intergalactic space, and even in what we might consider empty space. This field has a non-zero value everywhere, which is crucial for its mass-giving properties. When a fundamental particle, such as an electron, moves through this field, it interacts with it. This interaction is not a physical collision in the traditional sense, but rather a coupling. The strength of this coupling determines the particle's mass. Particles that interact strongly with the Higgs field, like the top quark, are very massive. Particles that interact weakly, like the electron, have very little mass. And then there are particles like the photon, the particle of light, which do not interact with the Higgs field at all, and therefore are massless, always traveling at the ultimate speed limit of the universe. The Higgs field is also responsible for the difference between the electromagnetic force and the weak nuclear force. At very high energies, these forces are unified. However, as the universe cooled after the Big Bang, the Higgs field switched on, breaking this symmetry and causing the forces to separate. This breaking of symmetry is a fundamental process that has shaped the very structure of the universe. It's a testament to how interconnected and elegant the fundamental laws of physics are. The Higgs field is not just a passive giver of mass. It is an active participant in the unfolding cosmic drama, a silent architect of the physical universe. Its influence is so pervasive that it shapes the very nature of matter, dictating how particles behave and interact, and ultimately, how structures like atoms, stars, and galaxies can come into being. It's a concept that challenges our everyday intuition, reminding us that the universe operates on principles far stranger and more beautiful than we might initially imagine. The subtle, ubiquitous presence of the Higgs field is a profound reminder that the universe is not merely a collection of objects, but a dynamic, interconnected web of forces and fields, each playing a crucial role in the grand cosmic tapestry. It is a fundamental aspect of our reality, a silent partner in the formation of all that we observe, and a key to understanding the very essence of matter itself. And so, the Higgs field, through its subtle, universal interaction, imbues the very essence of existence with weight, shaping the cosmos from the smallest quantum tremor to the grandest galactic swirl. Particles appear and disappear in the quantum foam. Imagine, if you will, peering into the very heart of existence, not at the solid, predictable world we experience daily, but at the fundamental, almost ethereal layer of reality. This is the realm of quantum mechanics, a domain where our common-sense notions of space, time, and matter begin to unravel, giving way to a tapestry of probabilities and fleeting possibilities. At this unimaginably small scale, the very fabric of spacetime is not smooth and continuous, but rather a roiling, bubbling sea, a chaotic effervescence known as the quantum foam. Within this foam, particles do not simply exist statically. They are born and they die, appearing and disappearing in a constant, energetic dance. This phenomenon is not a theoretical quirk. It is a direct consequence of Heisenberg's uncertainty principle, a bedrock of quantum physics. This principle states that certain pairs of properties of a particle, such as its position and momentum, cannot be known with perfect accuracy simultaneously. The more precisely we know one, the less precisely we can know the other. This inherent fuzziness has profound implications. Even in what we perceive as empty space, there are constant fluctuations in energy. According to Einstein's famous equation, E equals mc2, energy and mass are interchangeable. These energy fluctuations can, for fleeting moments, manifest as pairs of particles and antiparticles, such as an electron and a positron, popping into existence from the vacuum itself. These are called virtual particles. They exist for an infinitesimal fraction of a second, borrowing energy from the vacuum, only to annihilate each other and return that energy back to the void, restoring the vacuum to its seemingly empty state. It's as if the universe is constantly playing a game of creation and destruction, a cosmic breath of existence and non-existence, all happening at a speed and scale far beyond our direct perception. These virtual particles, though transient, are not without consequence. They mediate fundamental forces. For example, the electromagnetic force is understood as being carried by virtual photons. They influence the properties of real particles, contributing to phenomena like the Lamb shift in atomic energy levels, a subtle but measurable effect that validates the existence and importance of this quantum dance. The concept of empty space itself becomes redefined. It is not a passive void, but an active, dynamic environment, a vibrant medium teeming with potential, where the very building blocks of the universe are in a perpetual state of flux. This constant emergence and disappearance is a testament to the profound interconnectedness of energy, matter, and space-time, a fundamental characteristic of the universe at its deepest level. It suggests that even in the absence of what we might consider stuff, the universe is intensely alive, a vibrant symphony of creation and dissolution, a testament to the dynamic nature of reality itself. The energy that fuels this constant activity is immense, but because it is borrowed for such short durations, it remains hidden from our everyday experience, a secret whispered only to those who delve into the quantum realm. The quantum foam, therefore, is not merely a concept. It is a physical reality, a swirling, probabilistic substrate upon which the more stable, macroscopic universe is built. The fleeting existence of virtual particles is a constant reminder that the universe is far more fluid and dynamic than our macroscopic senses might suggest, a ceaseless interplay of being and non-being. In the silent ballet of the quantum foam, even nothingness teems with the ephemeral breath of existence, reminding us that all things in their briefest moments are born from the boundless sea of possibility. The universe operates on principles far beyond our everyday intuition. Our familiar world, the one we navigate with our senses, operates under rules that seem straightforward, almost self-evident. We understand gravity as a downward pull, time as a linear progression, and cause and effect as a direct chain. Yet, as we delve into the fundamental nature of reality, into the subatomic realm and the vast cosmic structures, we encounter phenomena that defy this common-sense understanding. At the quantum level, particles can exist in multiple states simultaneously, a concept known as superposition, where a particle is both here and there, spinning both ways, until an observation forces it to choose a single reality. This is not merely a theoretical oddity. It is the bedrock of quantum mechanics, describing the behavior of the universe at its most elemental. Furthermore, the principle of entanglement suggests that two particles once linked can instantaneously influence each other, regardless of the distance separating them. This spooky action at a distance, as Einstein famously called it, challenges our notions of locality and causality, implying a connectedness that transcends space and time as we perceive them. Imagine two coins, flipped simultaneously miles apart, always landing on opposite sides. That is a rudimentary analogy for entanglement, a phenomenon that suggests a deeper, more interconnected reality than our everyday experiences might suggest. Moving to the cosmic scale, we encounter the enigma of dark matter and dark energy. These invisible constituents make up an overwhelming majority of the universe's mass energy, yet their nature remains profoundly mysterious. Their gravitational effects on visible matter are undeniable, shaping the formation and dynamics of galaxies and galaxy clusters, but their direct detection has eluded us. This means that the universe we see, the stars, the planets, the nebulae, represents only a tiny fraction of what is actually out there, a testament to the vastness of our ignorance. The very expansion of the universe, too, is not a simple outward explosion into pre-existing space. Instead, space itself is stretching, carrying galaxies along with it, a concept that strains our intuition about motion and distance. The idea that space can expand, that the fabric of the cosmos can stretch and warp, is a concept born from Einstein's theory of general relativity, a theory that describes gravity not as a force, but as a curvature in space-time caused by mass and energy. This curvature dictates how objects move, and it also dictates how the universe as a whole evolves. The very notion of emptiness is also challenged by quantum physics. The vacuum, what we might intuitively consider to be nothingness, is in fact a dynamic sea of fluctuating quantum fields, where particles and antiparticles are constantly popping into and out of existence for fleeting moments. This quantum foam is a testament to the inherent activity and potential that underlies all of reality, even in what appears to be the void. The universe, therefore, is not a static stage upon which events unfold, but a dynamic, interconnected, and often paradoxical entity, governed by laws that are both elegant and profoundly alien to our everyday perceptions, urging us to expand our minds beyond the confines of what we can readily grasp. This universe, with its subatomic dances and cosmic stretches, whispers truths that our ordinary senses cannot fully comprehend, yet within its strangeness lies the profound beauty of existence. Even empty space is teeming with potential. We often perceive empty space as truly devoid of substance, a vast, silent void stretching between celestial bodies. It's a canvas upon which the grand dramas of the cosmos are painted, a seemingly inert backdrop to the vibrant dance of stars and galaxies. Yet this perception, so intuitive to our everyday experience, is a profound oversimplification. In the realm of quantum physics, what we call empty space is anything but. It is, in fact, a dynamic, energetic, and incredibly active environment, a constant hum of activity that underlies the very fabric of existence. Imagine a calm ocean surface. From a distance, it appears smooth and still. But dive beneath, and you find currents, life, and a constant flux of motion. Quantum vacuum is much like that, but on a scale so infinitesimally small that it defies our macroscopic imagination. At its heart, this concept stems from the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. This principle states that certain pairs of physical properties like position and momentum, or energy and time, cannot be known with perfect accuracy simultaneously. The more precisely you know one, the less precisely you can know the other. This inherent fuzziness, this fundamental uncertainty, has profound implications for the vacuum. It means that even in the absence of any real particles, the energy of a quantum field cannot be precisely zero. There must always be a minimum level of energy, a quantum fluctuation, that prevents these properties from being perfectly defined. This irreducible energy is what fills the vacuum, making it a sea of potential. These fluctuations manifest as the spontaneous creation and annihilation of virtual particles. These are not particles in the conventional sense that we can directly observe or measure for extended periods. Instead, they pop into existence for incredibly brief moments, borrowing energy from the vacuum, and then annihilate each other, returning that energy. This happens constantly, everywhere, in what is often referred to as the quantum foam. Think of it like bubbles forming and bursting on the surface of that ocean, but on a scale billions of times smaller than an atom. Electron-positron pairs, for instance, can briefly flicker into existence, only to recombine and vanish almost instantaneously. These virtual particles, though fleeting, have real, measurable effects. They influence the behavior of observable particles, contributing to phenomena like the Casimir effect, where two uncharged, parallel conductive plates placed very close together in a vacuum experience an attractive force. This force arises because the plates restrict the types of virtual particles that can exist between them, leading to a net pressure pushing the plates together compared to the more numerous virtual particles outside. Furthermore, these vacuum fluctuations are thought to be the seeds from which the large-scale structures of the universe, like galaxies and galaxy clusters, eventually grew during the inflationary epoch shortly after the Big Bang. The slight variations in energy density in the early universe, driven by these quantum fluctuations, were amplified by cosmic inflation, eventually becoming the gravitational anchors for matter to coalesce. So the seemingly empty void is, in fact, a vibrant, energetic medium, a reservoir of potential, constantly bubbling with activity that shapes the reality we perceive. It is the ultimate expression of the universe's inherent dynamism, a testament to the fact that even in stillness, there is profound motion and creation. And so, the quiet stillness we perceive is merely a surface, beneath which a universe of potential is perpetually and gracefully in motion. The energy density of the vacuum is astonishingly high. Consider for a moment the space around us. It feels empty, doesn't it? A void, a perfect, silent absence. Yet the universe, in its profound and often surprising nature, tells us a very different story. This seemingly empty space, this vacuum, is not a passive stage upon which cosmic events unfold. Instead, it is a dynamic, vibrant, and incredibly energetic entity. Quantum field theory, the bedrock of our understanding of the fundamental forces and particles, reveals that even in the absence of matter and energy as we typically perceive them, the vacuum itself possesses an inherent energy. This is known as vacuum energy, or sometimes zero-point energy. It arises from the constant, restless activity of quantum fields. These fields permeate all of space and time, and even when they are in their lowest energy state, their ground state, they are not truly at rest. Imagine them as a vast, cosmic ocean, perpetually rippling with a multitude of virtual particles. These virtual particles are not like the stable particles we observe, such as electrons or photons, which can persist for long periods. Instead, they pop into existence for fleeting moments, borrowing energy from the vacuum and then annihilate each other, returning that energy to the vacuum. This constant, ephemeral creation and annihilation process, happening everywhere all the time, imbues the vacuum with a substantial amount of energy. The implications of this are staggering. When cosmologists calculate the amount of energy density in the vacuum based on quantum field theory, the numbers are astronomically large, far exceeding what we observe in the form of matter and radiation in the universe. This discrepancy, known as the cosmological constant problem, is one of the greatest puzzles in modern physics. It suggests that our current understanding of quantum mechanics and gravity, while incredibly successful in their respective domains, may be incomplete or even fundamentally flawed when applied to the vast scales of the cosmos. However, even with this theoretical conundrum, the concept of vacuum energy remains a crucial component in our models of the universe. It is thought to be the driving force behind the accelerated expansion of the universe, a phenomenon that has reshaped our understanding of cosmic destiny. This unseen energy, inherent to the very fabric of spacetime, is not merely a theoretical curiosity. It is a fundamental aspect of reality, shaping the grand cosmic narrative. The universe, in its most fundamental state, is a realm of boundless, unseen potential, a testament to the fact that what appears empty is, in reality, brimming with an almost unimaginable power, a power that subtly nudges the very structure of existence on its grandest scales. Even the stillness of the void holds an immense, hidden power, a silent hum of creation that shapes the cosmos. Dark matter is an invisible scaffold holding galaxies together. Imagine a grand, cosmic city, its towering structures reaching out into the inky blackness, shimmering with the light of countless stars. We see these magnificent galaxies, swirling islands of light and gas, and we understand them as collections of stars, nebulae, and interstellar dust, all bound together by the familiar force of gravity, the very force that keeps our feet planted on the earth. But what if the visible matter, the stars and gas we can observe, is only a small fraction of what actually holds these celestial metropolises together? This is where the enigmatic concept of dark matter enters our understanding of the universe, a profound revelation that challenges our very perception of cosmic structure. For decades, astronomers have observed galactic behavior that simply doesn't align with the gravitational pull expected from visible matter alone. Stars on the outer edges of galaxies, for instance, orbit far too quickly. If only the visible mass were present, these stars should be flung out into the intergalactic void, like water from a spinning centrifuge. Yet, they remain steadfastly in their orbits, suggesting an unseen gravitational anchor, a pervasive, invisible scaffolding that provides the extra heft needed to keep galaxies intact. This unseen substance, dubbed dark matter, is theorized to be composed of particles that do not interact with light, or any electromagnetic radiation for that matter. They don't emit, absorb, or reflect light, making them utterly invisible to our telescopes, no matter how powerful. Yet their gravitational influence is undeniable. This invisible substance is not just a minor addition. Current estimates suggest that dark matter constitutes approximately 85% of the total matter in the universe. The visible matter, everything we can see and interact with, is merely the luminous tip of a much larger, darker iceberg. This vast, unseen mass forms a halo around galaxies, a diffuse, spherical distribution that extends far beyond the visible stellar disk. It's this dark matter halo that provides the dominant gravitational force, the invisible glue that binds the stars and gas within a galaxy, preventing them from dispersing. Think of it as the foundational bedrock upon which the visible city is built. Without this dark matter foundation, the luminous structures we admire would simply crumble. The discovery and study of dark matter have opened up an entirely new frontier in cosmology, pushing the boundaries of our knowledge and forcing us to reconsider the fundamental constituents of the cosmos. It's a testament to the universe's ability to surprise us, to reveal its grandest secrets through subtle gravitational whispers rather than flamboyant displays of light. The implications are staggering. The very architecture of the universe, the existence and stability of galaxies, are largely dictated by this elusive, invisible substance. It's a humbling realization that our familiar world of stars and planets is but a small, luminous detail within a much vaster, darker, and more profoundly structured cosmos. This invisible scaffolding dictates the formation and evolution of galaxies, shaping them over billions of years, guiding their mergers and interactions, and ultimately determining the cosmic landscape we observe today. The gravitational field of dark matter acts as a cosmic architect, drawing in ordinary matter and providing the framework for the formation of stars and, subsequently, galaxies. Without this pervasive dark matter, the universe might be a far more diffuse and less structured place, devoid of the magnificent galactic formations that inspire our awe. The very existence of complex structures like galaxies is a direct consequence of the gravitational pull exerted by this unseen component of the universe. It is the unseen hand that guides the cosmic dance, ensuring that the grand ballet of galactic formation and evolution can proceed as it has for eons. The ongoing quest to understand the nature of dark matter is one of the most pressing and exciting challenges in modern physics and astronomy, promising to unlock deeper truths about the fundamental forces and particles that govern our universe. Dark matter, like the silent roots of a great tree, provides the unseen strength that holds the luminous canopy of galaxies aloft. Galaxies are not isolated islands, but parts of a cosmic web. Imagine the universe as a vast, dark ocean, and within it, galaxies are like luminous islands, each a swirling collection of stars, gas, and dust. For a long time, our understanding of the cosmos painted this picture: individual galaxies, separated by immense stretches of emptiness, drifting in isolation. We saw them as distinct entities, each charting its own course through the cosmic void. But as our observational tools grew more powerful, and our ability to map the universe on grand scales improved, a more intricate and breathtaking reality began to emerge. The universe, it turns out, is not merely a collection of scattered islands, but a grand, interconnected tapestry, a cosmic web woven from the very fabric of space-time and the gravitational pull of matter. This cosmic web is the largest known structure in the universe, a filamentary network of galaxy clusters and superclusters, separated by vast, almost empty voids. These filaments, stretching for hundreds of millions of light years, are where the majority of galaxies reside. They are like cosmic highways, guiding the movement and evolution of galaxies. Within these filaments, galaxies are not alone. They are clustered together, drawn by gravity into groups, clusters, and superclusters. Our own Milky Way galaxy is part of the local group, a relatively small collection of about 50 galaxies, which in turn is part of the Virgo supercluster. And this supercluster is just one node in a much larger structure. The distribution of galaxies is not random. Instead, it follows a pattern that resembles a sponge or a honeycomb, with dense knots of galaxies at the intersections of filaments, and vast, largely empty regions, the cosmic voids, in between. These voids are not entirely devoid of matter. They still contain a diffuse intergalactic medium and a smattering of smaller galaxies, but they are significantly less dense than the filaments. The formation of this cosmic web is a direct consequence of the early universe's conditions and the laws of gravity. Tiny fluctuations in the density of matter in the very early universe, amplified over billions of years by gravity, led to the formation of these large-scale structures. Denser regions attracted more matter, growing into the filaments and clusters we observe today, while less dense regions became the vast voids. The gravity of dark matter, the invisible scaffolding of the universe, plays a crucial role in this process, providing the gravitational anchor for the visible matter to accumulate. This web is not static. It is a dynamic, evolving structure. Galaxies are constantly moving along these filaments, drawn towards denser regions, merging with their neighbors, or being flung out into the voids. The cosmic web is a testament to the profound interconnectedness of the universe, a reminder that even the grandest structures are part of a larger, unified whole, a cosmic dance of gravity and matter. In the grand cosmic tapestry, every galaxy is a thread, woven into a magnificent, interconnected web that spans the immensity of existence, reminding us that even in solitude, we are part of an infinitely larger, beautifully structured whole. The cosmic microwave background is an echo of creation. Imagine, if you will, a time so ancient, so fundamental that the very concept of time as we understand it was only just beginning to coalesce. This was the nascent universe, a blazing, opaque plasma, a searing inferno of energy and matter in constant, chaotic interaction. For hundreds of thousands of years, photons, the fundamental particles of light, were trapped within this dense soup, scattering off free electrons like billiard balls in a cosmic game, unable to travel more than a fleeting distance before colliding. The universe was a fog, a brilliant, impenetrable haze from which no clear image could emerge. But then, something extraordinary happened. As the universe continued its relentless expansion, it also cooled. Gradually, infinitesimally, the temperature dropped enough for a profound transformation to occur. Electrons, once unbound and energetic, found themselves captured by atomic nuclei, forming the first stable neutral atoms. This pivotal moment, known as recombination or decoupling, was a cosmic release. Suddenly, the photons were no longer perpetually scattered. They were free. They could, for the first time, travel unimpeded across the vast and ever-widening expanse of space. These liberated photons, carrying the imprint of that ancient, fiery epoch, began their journey outward, a journey that has continued for over 13 billion years. They have traversed unimaginable distances, stretched and cooled by the relentless expansion of the cosmos. What were once high-energy photons, characteristic of a universe millions of degrees hot, have been redshifted into the microwave portion of the electromagnetic spectrum, a gentle, pervasive hum that bathes the entire universe. This is the cosmic microwave background radiation, or CMB. It is not merely a faint glow. It is a snapshot, a fossilized fingerprint of the universe at its earliest discernible moment, a direct messenger from a time when the cosmos was a mere infant, brimming with the raw potential of everything that was yet to be. The CMB is the afterglow of the Big Bang, a testament to the universe's fiery birth, a cosmic lullaby sung by the universe itself, a faint whisper of the immense energies that once dominated existence. It is the oldest light we can possibly detect, a profound connection to the very origins of all that is. The patterns within this faint radiation, the subtle variations in temperature and polarization, are not random. They are the seeds from which all the structure we observe today, the galaxies, the stars, the planets, eventually grew. These tiny anisotropies, deviations from perfect uniformity, represent minuscule density fluctuations in that primordial plasma. Regions that were infinitesimally denser than their surroundings would eventually, under the relentless pull of gravity, draw in more matter, becoming the seeds of galaxy clusters and superclusters. Conversely, regions that were slightly less dense would expand more readily. The CMB, therefore, is not just an echo of creation. It is a map of the universe's initial conditions, a detailed blueprint of the cosmic architecture that was laid down in those earliest moments. Scientists meticulously study these patterns, using sophisticated telescopes and analytical techniques to understand the composition, age, and evolution of the universe. The CMB provides empirical evidence for the Big Bang theory, solidifying our understanding of cosmic history and guiding our exploration of the universe's deepest mysteries. It is a window into a time when the universe was a unified, incandescent entity, a time before the grand cosmic structures we see today had taken shape. The journey of these photons, from their liberation in the primordial plasma to their detection by our sensitive instruments, is a testament to the vastness of cosmic time and the enduring nature of light itself. The CMB is a constant reminder that we are all, in a very real sense, children of that ancient, fiery dawn, bathed in the light of creation. This ancient light, stretched by cosmic time, whispers the story of our universe's beginning, connecting us to the very first moments of existence. The universe is expanding, and the expansion is accelerating. Imagine, for a moment, a vast canvas stretching out in all directions, a canvas that is not static, not fixed, but alive, dynamic, and in a state of perpetual, gentle unfolding. For centuries, we looked up at the night sky and saw a celestial sphere, a collection of stars and nebulae seemingly fixed in their positions, a grand, unchanging tapestry. But then, through meticulous observation and profound insight, a revolutionary truth began to emerge, a truth that fundamentally altered our perception of everything. We discovered that the universe is not a still pond, but a boundless ocean, and this ocean is not merely moving, but actively and astonishingly expanding. This expansion isn't like a balloon inflating in a room where the surface stretches and distorts. Instead, it's as if the very fabric of space itself is growing, carrying galaxies along with it, not as objects moving through space, but as points on a stretching continuum. Think of raisins embedded in a loaf of dough that's rising. As the dough expands, every raisin moves away from every other raisin, and the further apart two raisins are, the faster they appear to recede from each other. This is a beautiful, albeit simplified, analogy for the cosmic dance we observe. Edwin Hubble in the early 20th century was one of the first to provide compelling evidence for this cosmic expansion. By observing the light from distant galaxies, he noticed a peculiar phenomenon. The light was consistently shifted towards the red end of the spectrum, a phenomenon known as redshift. This redshift is analogous to the Doppler effect we experience with sound. As a siren moves away from us, its pitch lowers, its sound waves stretching. Similarly, as galaxies move away from us, the wavelengths of their light are stretched, appearing redder. The further away a galaxy is, the greater its redshift, and thus, the faster it is receding. This observation led to Hubble's law, a cornerstone of modern cosmology, which states that the recessional velocity of a galaxy is directly proportional to its distance from us. This wasn't just a curious observation. It was a profound revelation, suggesting that the universe itself is growing larger, that the distances between cosmic structures are increasing over time. It implies that if we were to rewind the cosmic clock, all these galaxies would have been much closer together, converging towards a single point in the distant past, the genesis of the Big Bang. But the story doesn't end with simple expansion. In the late 1990s, a series of groundbreaking observations, primarily focusing on distant supernovae, revealed an even more astonishing truth. The expansion of the universe is not only happening, but it is accelerating. This was a discovery that sent ripples of surprise and excitement through the scientific community, challenging existing models and prompting new avenues of inquiry. It meant that the gravitational pull of all the matter in the universe, which we might expect to be slowing down this expansion, is actually being overcome by some other, more potent force. This accelerating expansion suggests that the universe is not destined to slow down and eventually collapse back upon itself, but rather to continue expanding indefinitely, perhaps even at an ever-increasing rate. The implications of this acceleration are vast and deeply philosophical. It points towards the existence of a mysterious entity, a form of energy inherent in space itself, that acts as a sort of cosmic anti-gravity, pushing everything apart. This enigmatic force has been dubbed dark energy, and it is estimated to constitute about 70% of the total energy density of the universe, making it the dominant component of our cosmos, yet remaining largely unknown. Understanding the nature of dark energy is one of the greatest challenges facing contemporary physics and cosmology. Is it a cosmological constant, as Einstein once proposed, a fixed energy density inherent to the vacuum of space? Or is it something more dynamic, a field that changes over time and space? The accelerating expansion is not a localized phenomenon. It is a universal characteristic. Every distant galaxy, every cluster of galaxies, is being carried away from every other on this expanding fabric. This cosmic acceleration paints a picture of a universe that is not only immense and ancient, but also imbued with a hidden dynamism, a relentless outward push that shapes its ultimate destiny. It's a reminder that our understanding of the cosmos is an ongoing journey, a continuous unveiling of its profound and often surprising characteristics. The universe is not merely vast, but is actively growing, a cosmic breath that expands our perspective and whispers of unseen forces shaping our collective destiny. Dark energy is the mysterious force driving this expansion. Imagine the universe not as a static painting, but as a vast, dynamic canvas, constantly stretching and unfurling. For a long time, astronomers believed that gravity, the universal force of attraction, would eventually slow down this cosmic expansion, perhaps even reversing it, leading to a grand cosmic collapse. But as our observational capabilities grew, and as we peered deeper into the cosmos, a startling revelation emerged. The universe isn't just expanding, it's expanding at an ever-increasing rate. This acceleration, this cosmic push, is so profound that it suggests the existence of a force counteracting gravity on the grandest scales. This enigmatic entity, this cosmic propellant, has been given a name: dark energy. It's a term that reflects our current state of understanding. We know it's there because we see its effect, but its true nature remains one of the most profound mysteries in modern physics. Dark energy is thought to constitute approximately 68% of the total energy density of the universe, making it the dominant component of our cosmos. This is a staggering proportion, considering that ordinary matter, the stuff that makes up stars, planets, and ourselves, accounts for only about 5%. Even dark matter, the invisible scaffolding that holds galaxies together, makes up a mere 27%. So the universe is, for the most part, composed of something we cannot directly see, touch, or fully comprehend. The most widely accepted theoretical explanation for dark energy is the cosmological constant, a concept first introduced by Albert Einstein in his theory of general relativity. Einstein initially invoked this constant to maintain a static universe, a view prevalent at the time. However, when Edwin Hubble discovered the universe's expansion, Einstein famously called his cosmological constant his biggest blunder. Yet, with the discovery of accelerated expansion, this blunder has been resurrected, albeit with a different interpretation. The cosmological constant, often denoted by the Greek letter lambda, represents an intrinsic energy density of empty space itself. According to quantum field theory, even what we perceive as a vacuum is not truly empty. It is a seething, frothing sea of virtual particles constantly popping into and out of existence. These quantum fluctuations, it is theorized, could possess a constant energy, and this energy would exert a repulsive gravitational effect, pushing space-time apart. If this vacuum energy is indeed the source of dark energy, its density would be uniform throughout the universe and would not dilute as the universe expands, unlike matter or radiation. This unchanging density is crucial for explaining the observed acceleration. As the universe expands, the amount of matter and radiation within a given volume decreases, their influence weakening. But if dark energy is a property of space itself, then as more space is created, more dark energy comes into being, maintaining its density and its outward push. However, there's a significant theoretical hurdle. When physicists try to calculate the expected energy density of the vacuum based on quantum field theory, the result is astronomically larger than what is observed, by a factor of 10 to the power of 120, an almost unimaginable discrepancy. This cosmological constant problem is one of the most significant challenges facing theoretical physics. It suggests that our current understanding of quantum mechanics and gravity, or both, is incomplete. Other theoretical possibilities for dark energy include quintessence, a hypothetical dynamic energy field that permeates space and could change in density and pressure over time, or modifications to Einstein's theory of gravity itself, suggesting that gravity behaves differently on cosmic scales than predicted. The implications of dark energy are profound. If it continues to dominate the universe, it suggests a future where galaxies become increasingly isolated from one another. As the expansion accelerates, the light from distant galaxies will eventually be redshifted so severely that they will disappear from our observable horizon, leaving our own galaxy, the Milky Way, and its immediate neighbors as an island universe, surrounded by an ever-expanding void. This scenario, known as the Big Rip, is one possibility, though less likely if dark energy is a true cosmological constant. More probable is a scenario where the expansion continues indefinitely, leading to a cold, dark, and empty universe. The ongoing quest to understand dark energy is not merely an academic pursuit. It is a fundamental inquiry into the very fabric and destiny of our cosmos. It is a testament to the universe's capacity for surprise, revealing that the most dominant force shaping our reality is also the most elusive. And so, this unseen force, this silent architect of cosmic acceleration, reminds us that the grandest narratives are often written in the subtlest of strokes, in the very emptiness that surrounds us. The fate of the universe depends on these unseen forces. The grand narrative of our cosmos, from its explosive birth to its eventual, unfathomable end, is not a story written in stone, but rather a delicate, ongoing negotiation between fundamental forces, many of which remain shrouded in mystery. For eons, humanity has gazed at the stars, pondering our place and the ultimate destiny of everything we know. We've charted the movements of celestial bodies, understood the life cycles of stars, and even begun to comprehend the intricate dance of galaxies. Yet, at the very heart of the universe's grand unfolding lie two enigmatic entities, dark matter and dark energy. These are not mere theoretical curiosities. They are the primary architects of the cosmic future, silently dictating the universe's trajectory. Dark matter, while invisible and undetectable by conventional means, exerts a profound gravitational influence. It acts as the cosmic scaffolding, holding galaxies together, preventing them from spinning themselves apart. Without its unseen embrace, the very structures we observe, the majestic spirals of galaxies, the clustered formations of galaxy clusters, would likely never have coalesced. Its presence is inferred, not seen, a testament to the pervasive power of gravity even when the source is hidden. But it is dark energy that truly holds the reins of the universe's ultimate fate. In the late 1990s, observations of distant supernovae revealed a startling truth. The expansion of the universe is not slowing down, as gravity would suggest, but is instead accelerating. This acceleration implies the existence of a repulsive force, a cosmic anti-gravity, pervading all of space. This is dark energy, a phenomenon that currently accounts for roughly 70% of the universe's total energy density. Its nature is perhaps the greatest puzzle in modern cosmology. Is it a constant energy inherent to space itself, a cosmological constant as Einstein once theorized? Or is it something more dynamic, a field that changes over time and space? The answer to this question has profound implications. If dark energy is a constant, then the universe will continue to expand at an ever-increasing rate. Galaxies will recede from each other at speeds exceeding the speed of light, eventually becoming causally disconnected. The night sky, as we know it, would fade into an empty, featureless void, leaving only our local galactic neighborhood in an ever-expanding bubble of isolation. This scenario, often termed the Big Freeze or heat death, paints a picture of a cold, dark, and ultimately quiescent universe. However, if dark energy is not constant, if it strengthens over time, a more dramatic end might await. This hypothetical scenario, known as the Big Rip, suggests that the accelerating expansion would eventually become so powerful that it would overcome all fundamental forces, tearing apart galaxies, stars, planets, and even atoms themselves. Imagine a cosmic unraveling, a violent disintegration of all structure. Conversely, if dark energy were to weaken or even reverse its effect, the universe might eventually halt its expansion and begin to contract, leading to a big crunch, a reversal of the Big Bang, where all matter and energy would collapse back into an infinitely dense point. The delicate balance between the attractive force of gravity, amplified by dark matter, and the repulsive push of dark energy is the cosmic seesaw upon which our universe's destiny is precariously balanced. Our current understanding, based on the most precise cosmological measurements, favors the Big Freeze scenario, where the universe continues its relentless expansion into a cold, dark, and empty future. Yet, the very fact that these dominant forces remain largely unknown underscores the vastness of our ignorance and the humbling reality that the grandest narratives of existence are still being written by invisible hands. These unseen forces are not just abstract concepts. They are the silent conductors of the cosmic symphony, determining whether the universe will fade into eternal stillness, tear itself asunder, or perhaps, in ways we cannot yet fathom, find a different, unexpected conclusion. The unseen forces of dark matter and dark energy are the silent arbiters of our cosmos's ultimate fate, weaving a story of expansion and isolation, or perhaps something far more dramatic. Stars are nuclear furnaces, forging the elements we are made of. At the heart of every star, a colossal furnace burns, not with flame but with the raw power of nuclear fusion. These celestial bodies, scattered across the immeasurable canvas of the cosmos, are the universe's alchemists, transforming the simplest of elements into the very building blocks of everything we know, and indeed everything we are. Imagine, for a moment, the intense pressure and heat that exist within the core of a star. We are talking about conditions so extreme that the nuclei of atoms are forced together, overcoming their natural repulsion to merge and create new, heavier elements. This process, nuclear fusion, is the engine that powers stars, releasing an immense amount of energy in the form of light and heat, which then radiates outward across the vast emptiness of space, eventually reaching our own distant planet. The story begins with the most abundant element in the universe, hydrogen. In the stellar core, under unimaginable gravitational pressure, hydrogen nuclei, which are essentially single protons, are compelled to collide and fuse. The primary process, known as the proton-proton chain, involves several steps where hydrogen nuclei are converted into helium. This is the most common fusion pathway in stars like our Sun. As hydrogen is consumed, helium accumulates in the star's core. When the hydrogen fuel in the core is depleted, the star's structure begins to change. The core contracts under gravity, and the outer layers expand, leading to the formation of a red giant or a red supergiant, depending on the star's initial mass. But the stellar alchemy doesn't stop at helium. For more massive stars, the journey continues. As the core contracts further, the temperature and pressure rise to even greater heights, becoming sufficient to fuse helium nuclei together. This process, called the triple alpha process, creates carbon. Carbon, in turn, can fuse with another helium nucleus to form oxygen. And so the chain reaction continues, with elements like neon, magnesium, silicon, and finally, iron, being forged in the cores of these stellar furnaces. Each stage of fusion requires progressively higher temperatures and pressures, and each stage produces heavier elements. However, there is a crucial turning point: iron. Iron is the most stable atomic nucleus. Fusing iron nuclei together does not release energy. Instead, it requires asterisk energy. This means that when a star's core becomes predominantly iron, the fusion process that has been supporting it against gravitational collapse grinds to a halt. The star can no longer generate the outward pressure needed to counteract the inward pull of its own immense gravity. This is the prelude to a catastrophic event. For stars significantly more massive than our Sun, the iron core's collapse triggers a supernova explosion. This is one of the most energetic events in the universe, a cosmic detonation that briefly outshines entire galaxies. During the supernova, the immense energy released and the sudden influx of neutrons create an environment where elements heavier than iron can be rapidly synthesized. This includes elements like gold, silver, lead, and uranium. So the very atoms that make up our bodies, the iron in our blood, the calcium in our bones, the carbon in our DNA, and the trace elements that give flavor to our food, were all born in the fiery hearts of stars that lived and died billions of years ago. We are, quite literally, stardust. The universe, in its grandest and most violent displays, has meticulously crafted the materials that allow life to exist, weaving our very essence from the ashes of ancient stellar explosions. The cosmic forge of stars, through relentless fusion and explosive finales, has meticulously crafted the elemental tapestry of existence, gifting us the very substance of our being from their incandescent demise. The life cycle of stars is a grand cosmic ballet. Stars, those distant points of light that adorn our night sky, are far more than mere celestial decorations. They are dynamic, evolving entities, each with its own unique story of birth, life, and eventual demise. This grand cosmic ballet, played out over eons and across unimaginable distances, is a fundamental process shaping the very elements that compose everything we know, including ourselves. At its heart, a star's life is a continuous battle between two opposing forces: gravity, which seeks to collapse the star inward, and the outward pressure generated by nuclear fusion in its core, which resists this collapse. This delicate equilibrium dictates the star's existence, its luminosity, its temperature, and ultimately its fate. The journey begins within vast, cold clouds of gas and dust, primarily hydrogen and helium, known as nebulae. These nebulae are not static. They are stirred by the shockwaves of nearby supernovae, gravitational tugs from passing stars, or the general turbulence of interstellar space. These disturbances cause regions within the nebula to become denser. As these denser pockets accumulate more matter, their gravitational pull increases, drawing in even more surrounding material. This process of accretion continues, causing the core of the collapsing cloud to heat up. As the temperature and pressure rise, the atoms of hydrogen begin to collide with enough force to overcome their natural repulsion. This is the genesis of nuclear fusion. When the core reaches a critical temperature and density, typically around 10 million degrees Celsius, hydrogen atoms begin to fuse, transforming into helium. This fusion releases an immense amount of energy in the form of photons and neutrinos. This energy, pushing outward from the core, counteracts the inward pull of gravity, and a star is born. The star then settles into its main sequence phase, a period of stability that can last for billions of years, depending on its mass. Our own Sun, a relatively average star, is currently in its main sequence phase. The mass of a star is the single most crucial factor determining its life cycle and its ultimate destiny. Low-mass stars, like red dwarfs, fuse hydrogen very slowly and can live for trillions of years, outlasting the current age of the universe. They will eventually fade into white dwarfs. Intermediate-mass stars, like our Sun, will also eventually shed their outer layers, forming beautiful planetary nebulae, and their cores will contract into white dwarfs. However, it is the high-mass stars, those born with many times the mass of our Sun, that perform the most dramatic and spectacular acts in this cosmic ballet. As these massive stars exhaust their hydrogen fuel, they begin to fuse heavier elements in their cores, helium into carbon, carbon into oxygen, and so on, all the way up to iron. Iron is a critical turning point because fusing iron does not release energy. Instead, it absorbs it. When the core of a massive star becomes predominantly iron, the outward pressure from fusion ceases. Gravity then takes over with unstoppable force. The core collapses catastrophically in a fraction of a second, triggering a colossal explosion known as a supernova. This explosion is so powerful that it can outshine an entire galaxy for a brief period, scattering newly forged heavy elements like gold, silver, and uranium across the cosmos. The remnant left behind after a supernova depends on the initial mass of the star. If the star was massive enough, the core will collapse into an incredibly dense neutron star, a city-sized object composed almost entirely of neutrons. If the star was exceedingly massive, even the neutron star cannot withstand the gravitational collapse, and it will shrink into a black hole, a region of spacetime where gravity is so strong that nothing, not even light, can escape. Thus, the stellar life cycle, from the gentle ignition of a protostar to the violent cataclysm of a supernova or the silent mystery of a black hole, is a profound testament to the universe's capacity for both creation and destruction, weaving the very fabric of our existence from stardust. Neutron stars are the densely packed remnants of stellar explosions. Imagine a star, far more massive than our own Sun, reaching the end of its luminous life. It has exhausted its nuclear fuel, the very engine that sustained its outward pressure against the relentless inward pull of its own gravity. When this happens, the star's core collapses catastrophically. The immense gravitational forces crush the atoms, forcing protons and electrons to combine, forming neutrons. This process is so violent, so incredibly energetic, that it triggers a spectacular supernova explosion, blasting the star's outer layers out into the cosmos. But at the heart of this cosmic inferno, something extraordinary remains: a neutron star. These are not merely dead stars. They are some of the densest objects known to exist in the universe. To comprehend their density, consider this. A single teaspoon of neutron star material would weigh as much as Mount Everest. If you could hypothetically hold a sugar cube's worth of a neutron star, it would weigh more than all the cars on Earth combined. The gravitational pull at the surface of a neutron star is billions of times stronger than Earth's. If you were to stand on one, you would be instantly flattened into a microscopic layer of matter. The neutrons within them are packed so tightly that they form a kind of quantum fluid, behaving in ways that defy everyday experience. These stars are typically only about 20 kilometers or 12 miles in diameter, yet they can contain more mass than our Sun. Their magnetic fields are also staggeringly powerful, trillions of times stronger than Earth's, capable of influencing the surrounding space in profound ways. Some neutron stars, known as pulsars, rotate incredibly rapidly, spinning hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles. If these beams sweep across our line of sight as they rotate, we observe them as regular pulses of radio waves, hence the name pulsar. These celestial objects, born from the violent death of a giant star, are cosmic marvels of extreme physics, a testament to the universe's capacity for creating the most astonishing and compact forms of matter. Within the heart of a collapsed star, a new, incredibly dense entity is born, a neutron star, holding the universe's ultimate compression in its quiet, pulsating existence. Black holes warp spacetime, bending light itself. Imagine a place where the very fabric of reality, the stage upon which all events unfold, is so profoundly distorted that even light, the fastest thing in the cosmos, cannot escape its embrace. This is the realm of black holes, cosmic enigmas that challenge our deepest intuitions about space and time. At their heart lies the principle of spacetime curvature, a concept first elegantly described by Albert Einstein's theory of general relativity. This theory posits that gravity is not a force acting across a distance, but rather a manifestation of the curvature of spacetime itself. Massive objects like stars and planets create dips and valleys in this cosmic fabric, and it is this warping that dictates how other objects move. Now, consider an object of unimaginable density, a collapsed star so massive that its gravitational pull becomes absolute. This is a black hole. The mass is concentrated into an infinitely small point, a singularity, and around this singularity is a boundary known as the event horizon. This is not a physical surface, but rather a point of no return. Once anything, including light, crosses the event horizon, it is irrevocably drawn towards the singularity. The warping of spacetime here is so extreme that all paths, all possible trajectories, lead inward. Light, which travels in straight lines through normal spacetime, is forced to follow these curves, and within the event horizon, all these curves lead to the center. This bending of light is not just theoretical, it has been observed. Gravitational lensing, where the gravity of massive objects bends the light from more distant objects, is a direct consequence of space-time curvature. Black holes, being the most extreme examples of mass concentration, are powerful gravitational lenses. They can distort, magnify, and even create multiple images of background objects. The light from a star behind a black hole might be bent around it, appearing to us as a ring or an arc. This phenomenon allows us to indirectly detect and study these elusive objects, even though we cannot see them directly. The very existence of black holes, these cosmic drains, suggests a universe far more dynamic and mysterious than we might initially perceive. They are not just points of destruction, but also laboratories for extreme physics, pushing the boundaries of our understanding of gravity, space, and time. The warped spacetime around a black hole is a testament to the profound interconnectedness of mass and geometry, where the universe itself bends and reshapes in response to the presence of immense density. It is a reminder that the cosmos operates on scales and principles that can both humble and inspire, a grand, silent testament to the extraordinary forces at play. The bending of light by a black hole is a cosmic ballet of warped dimensions, reminding us that even in the deepest darkness, the universe reveals its profound and elegant laws. Supermassive black holes reside at the centers of most galaxies. At the heart of nearly every galaxy, from the grand spirals we can readily observe to the more diffuse elliptical giants, lies an entity of unimaginable power and mystery, a supermassive black hole. These colossal cosmic engines are not mere curiosities. They are fundamental architects of galactic structure and evolution. Imagine a gravitational singularity so dense that nothing, not even light, can escape its clutches. These are not the stellar mass black holes that form from the collapse of individual stars. These are behemoths, millions, even billions of times the mass of our Sun. Their existence at the core of galaxies is not an accident but a profound consequence of the universe's formation and ongoing processes. The prevailing theory suggests that these supermassive black holes grew over cosmic time, accreting vast amounts of gas, dust, and even entire stars. They may have begun as smaller seed black holes, perhaps formed from the collapse of the very first massive stars in the early universe, and then steadily grew by swallowing everything in their path. The sheer scale of this accretion is difficult to grasp. Consider the Milky Way, our own galaxy. At its center, we find Sagittarius A*, a supermassive black hole approximately 4 million times the mass of our Sun. While this might seem immense, it is relatively modest compared to some of the cosmic giants out there. The galaxy M87, for instance, boasts a supermassive black hole with a mass of over 6 billion suns. These gargantuan objects are not just passive inhabitants of galactic centers. They actively influence their surroundings. When gas and dust fall towards a supermassive black hole, they form an accretion disk, a swirling vortex of superheated material. As this material spirals inward, it can release tremendous amounts of energy in the form of radiation and powerful jets of particles. These energetic outflows, known as active galactic nuclei, AGN, or quasars when particularly luminous, can have a profound impact on the galaxy itself. They can heat up or even expel the gas within the galaxy, regulating star formation and shaping the galaxy's morphology. Without these central behemoths, galaxies might have evolved very differently, perhaps becoming much larger and forming stars at a far more rapid rate. The presence of supermassive black holes is a testament to the universe's capacity for extreme phenomena and its intricate, self-regulating processes. They are the silent, all-consuming hearts of galaxies, pulling in the cosmic dust and gas, dictating the rhythm of star birth, and ultimately shaping the very structure of the celestial bodies we observe across the vastness of space. The very existence of these galactic anchors, invisible yet undeniably powerful, reminds us that the universe is a place of profound contrasts, where the most destructive forces can also be the most creative. In the silent, swirling heart of every cosmic island, a gravitational titan slumbers, a testament to the universe's power to forge the ultimate anchors of existence. The Milky Way galaxy is a vast spiral of billions of stars. Our home, the Milky Way, is not a solitary wanderer in the cosmic dark, but a majestic, sprawling metropolis of stars, gas, and dust, a grand spiral structure that holds within its arms an estimated 100 to 400 billion stars. Imagine, if you can, a celestial city so immense that traversing it from one edge to the other would take tens of thousands of years, even if you could travel at the speed of light, the fastest speed known to physics. This vastness is not merely a matter of size, but of intricate structure and dynamic activity. The Milky Way is classified as a barred spiral galaxy, meaning its central region, a bulge of older stars, is elongated into a bar shape, from which two major spiral arms, and several minor ones, emerge and gracefully curve outwards. These arms are not solid, static entities, but rather dynamic regions where star formation is most active. Within these luminous rivers of gas and dust, nebulae, colossal clouds of hydrogen and helium, often illuminated by the intense radiation of nearby young, hot stars, are the stellar nurseries, the birthplaces of new suns. Our own sun, a rather ordinary G-type main-sequence star, is located in one of these arms, the Orion Arm, also known as the Orion Spur, a relatively quiet, interstellar neighborhood about two-thirds of the way out from the galactic center. The galactic center itself is a region of intense gravitational pull and activity, dominated by a supermassive black hole, Sagittarius A, whose gravitational influence shapes the orbits of stars and gas clouds in its vicinity. This central bar and bulge are densely packed with older, redder stars, hinting at an ancient history, while the spiral arms are characterized by younger, bluer, and hotter stars, along with the aforementioned nebulae, painting a picture of ongoing creation and renewal. The entire structure is enveloped in a faint, diffuse halo of dark matter, an invisible scaffolding that provides the gravitational anchor for the visible components, and within which reside ancient, globular clusters, dense, spherical collections of hundreds of thousands, or even millions of old stars. The sheer number of stars is almost incomprehensible, each a distant sun, potentially with its own planetary system, each a unique story in the grand cosmic narrative. The gas and dust that permeate the galaxy, known collectively as the interstellar medium, are crucial for the ongoing cycle of stellar birth and death, being recycled through supernovae explosions and stellar winds to form new generations of stars and planets. The scale of this galactic ecosystem is a testament to the universe's capacity for immense, complex structures, and our place within it, though seemingly small, is deeply interconnected with this grand celestial ballet. The light we see from distant stars in our own galaxy has traveled for thousands, even tens of thousands of years to reach us, meaning we are looking into the past, observing these celestial bodies as they were long ago. This constant interplay of gravity, star formation, and stellar evolution across billions of stars creates a dynamic and ever-changing panorama, a cosmic dance that has been ongoing for billions of years and will continue for billions more. Within this vast spiral, our sun is but a single spark, a luminous reminder that even the grandest structures are composed of countless individual wonders, each contributing to the breathtaking tapestry of our home galaxy. Our solar system is a tiny speck in the galactic expanse. Imagine for a moment the grand tapestry of our Milky Way galaxy. It is a colossal, luminous island in the vast ocean of the cosmos, a swirling disk of stars, gas, and dust, stretching across an unimaginable distance. Within this breathtaking structure, our solar system, with its sun, its planets, its moons, asteroids, and comets, is not even a single grain of sand on an endless beach. It is, in fact, far, far smaller than that. To truly grasp this, we must first consider the sheer scale of the Milky Way itself. Our galaxy is estimated to contain somewhere between 100 billion and 400 billion stars. That is a number so immense it begins to blur the edges of our comprehension. Each of these stars, like our own sun, could potentially host its own planetary system, its own collection of orbiting worlds. The diameter of the Milky Way is estimated to be around 100,000 to 120,000 light years. A light year, remember, is the distance light travels in 1 year, a staggering 9.46 trillion kilometers. So, to traverse our galaxy from one edge to the other would take light itself over 100,000 years. Now, where does our solar system fit into this? Our sun, a relatively average star, is located about 2/3 of the way out from the galactic center, in one of the galaxy's spiral arms, known as the Orion Arm. The distance from the sun to the center of the Milky Way is approximately 26,000 light years. This means that even to reach the heart of our own galaxy, light would need to travel for 250,000 years. And our solar system, with its entire collection of planets, is contained within a region that, relative to the galaxy's immense diameter, is infinitesimally small. If we were to shrink the entire Milky Way down to the size of a large dinner plate, our solar system would be smaller than a single bacterium on that plate. The distances within our solar system, which seem so vast to us, are mere pinpricks when viewed against the backdrop of our galactic home. The farthest planet, Neptune, is about 30 astronomical units from the Sun, where 1 AU is the distance from the Earth to the Sun. This is about 4.5 billion kilometers. To put that in perspective, if the Sun were the size of a grapefruit, Neptune would be a tiny speck of dust orbiting a few meters away. Now, consider that this entire vast, yet comparatively minuscule, system is hurtling through space at an incredible speed. Our solar system orbits the galactic center at a speed of about 230 kilometers per second, or 828,000 kilometers per hour. At this speed, it takes our solar system approximately 230 million years to complete one orbit around the Milky Way. This period is known as a galactic year. So, in the entire history of our solar system, it has only completed about 20 such orbits. This constant motion, this ceaseless journey through the galactic void, further emphasizes our system's dynamic yet contained nature within the grander cosmic dance. The stars that appear to us as brilliant points of light in the night sky are, in fact, suns like our own, many of them vastly larger and brighter, separated by distances that dwarf our solar system's dimensions. The nearest star system to our own, Alpha Centauri, is over 4 light-years away. That's approximately 40 trillion kilometers. If our solar system were the size of a coffee mug, Alpha Centauri would be another coffee mug many kilometers away. The sheer emptiness between stars and the immense distances between stellar systems is a profound testament to the scale of the galaxy. We are nestled within a vast, swirling structure, a cosmic city of stars, and our immediate neighborhood is but a tiny, quiet corner of this immense metropolis. The feeling of being small is not a diminishment, but an invitation to appreciate the breathtaking scope of our cosmic dwelling. And so, our solar system, a mere whisper in the galactic wind, orbits its star, a tiny, precious bubble of existence within the immense, luminous embrace of the Milky Way, a reminder that even in our apparent insignificance, we are part of something profoundly majestic. The nearest star system is still light years away. Even as we gaze up at the night sky, filled with what appears to be a dense tapestry of stars, a profound truth often remains just beyond our immediate grasp: the sheer, almost unimaginable distance that separates us from our closest stellar neighbors. The concept of a light year, while a fundamental unit in astronomy, can be difficult to truly internalize. It's not a measure of time, but of distance. The distance that light, the fastest thing in the universe, travels in 1 year. Light zips through the vacuum of space at approximately 299,792 kilometers per second, or about 186,282 miles per second. To put that into perspective, in just 1 second, light could circle the Earth more than 7 times. Now, imagine that speed sustained for an entire year. That's the length of a light year. Our sun, of course, is our closest star, and the light we see from it takes about 8 minutes to reach us. But beyond our sun, the next closest star system is Proxima Centauri, part of the Alpha Centauri triple star system. Proxima Centauri is a red dwarf star, much smaller and dimmer than our sun, and it is approximately 4.24 light-years away. This means that the light we are observing from Proxima Centauri today began its journey towards us over 4 years ago. If we were to send a spacecraft to Proxima Centauri traveling at speeds comparable to our fastest current probes, like the Voyager spacecraft, it would take tens of thousands of years to reach it. This vast gulf of space is not empty. It is filled with the tenuous interstellar medium, a diffuse gas and dust that, while incredibly sparse, still represents a significant obstacle and a testament to the sheer emptiness of the void between stars. The nearest star, Proxima Centauri, is not a solitary entity. It is part of a gravitationally bound system with 2 other stars, Alpha Centauri A and Alpha Centauri B, which orbit each other. These 2 larger stars are slightly farther away, around 4.37 light-years. The entire Alpha Centauri system, though our closest stellar neighbor, is still an immense distance from our own solar system. To comprehend this distance, consider that if our solar system were the size of a large coin, Proxima Centauri would be on another continent. The sheer scale of these distances underscores our isolation, not in a lonely sense, but in a way that highlights the preciousness and uniqueness of our own cosmic home. It reminds us that the stars we see are not just points of light, but distant suns, each with its own planetary systems, separated by gulfs of space so vast that our minds can barely comprehend them. Even our closest stellar neighbors are so profoundly distant that the light reaching us now left them when our present-day world was still a distant dream. The nearest star, though a mere whisper away on a cosmic scale, remains an immense journey, reminding us of the profound isolation and vastness that defines our place in the universe. Exoplanets orbit countless stars, hinting at universal abundance. The discovery of planets beyond our solar system, exoplanets, has fundamentally reshaped our understanding of the cosmos, transforming our perception of Earth's place within it from a unique anomaly to potentially one among a staggering multitude. For millennia, our gaze was confined to the celestial bodies that danced within our own solar neighborhood: the sun, the moon, the five visible planets, and the distant, unblinking stars. These stars were largely perceived as fixed points of light, decorative elements in the grand tapestry of the night sky. Their true nature, and the possibility of worlds orbiting them, remaining within the realm of philosophical speculation and science fiction. However, the advent of advanced astronomical instrumentation and sophisticated detection techniques has unveiled a universe far richer and more populated than we could have ever imagined. We now know with an ever-increasing certainty that our sun is not a solitary star hosting a planetary entourage. Instead, it is one of billions, perhaps trillions, of stars scattered across our galaxy alone, and our galaxy, the Milky Way, is but one of countless galaxies in the observable universe. And crucially, a significant fraction of these distant suns are accompanied by their own planetary systems. The methods by which we detect these distant worlds are ingenious testaments to human curiosity and scientific rigor. The transit method, perhaps the most successful to date, relies on observing the slight dip in a star's brightness as a planet passes in front of it from our vantage point. This subtle dimming, a mere fraction of a percent, can reveal the presence and even the size of an orbiting planet. Another key technique is the radial velocity method, which detects the tiny wobble in a star's motion caused by the gravitational tug of an orbiting planet. As a planet orbits, it pulls on its host star, causing the star to move slightly back and forth, a movement that can be detected by observing shifts in the star's light spectrum. Gravitational microlensing, a phenomenon predicted by Einstein's theory of general relativity, offers another powerful tool, where the gravity of a foreground star and its planet bends and magnifies the light from a more distant star, revealing the presence of the unseen planetary companion. These methods and others have collectively identified thousands of confirmed exoplanets, with many thousands more candidates awaiting confirmation. What these discoveries reveal is a breathtaking diversity of planetary systems. We have found gas giants larger than Jupiter, rocky worlds comparable in size to Earth, planets orbiting incredibly close to their stars, completing their orbits in mere days, and others that reside in the habitable zone, the region around a star where liquid water could potentially exist on a planet's surface. The sheer number of exoplanets detected suggests that planet formation is not a rare cosmic accident, but a common, perhaps even inevitable, outcome of stellar evolution. If planets are so common, then the question of whether life exists elsewhere in the universe transitions from a philosophical debate to a statistical probability. The abundance of exoplanets, each a potential world with its own unique history and chemistry, fuels our imagination and underscores the vastness of cosmic possibility, suggesting that the universe is not a desolate void but a fertile ground for worlds and perhaps for life itself. The vastness of the cosmos, populated by countless orbiting worlds, suggests that our existence is not a singular, isolated event, but a potential thread woven into a grand, universal tapestry of planetary cradles. The search for extraterrestrial life is a quest for cosmic kinship. Our gaze turns outward, not just to the grand architecture of the cosmos, but to its potential inhabitants. The search for extraterrestrial life, often framed as a scientific endeavor to detect signals or biosignatures, is, at its heart, a profound philosophical quest for cosmic kinship. It's an echo of humanity's oldest questions. Are we alone? What is our place in this immense tapestry of existence? When we scan the heavens with our radio telescopes, listening for the faintest whisper from a distant star, we are not merely seeking scientific data. We are reaching out, tentatively, across the vast gulfs of space and time, hoping for a response that would fundamentally alter our understanding of ourselves and our universe. This pursuit is driven by an innate curiosity, a deep-seated yearning to connect, to find affirmation that life, in its myriad forms, is not a singular accident confined to our pale blue dot, but perhaps a ubiquitous and fundamental characteristic of the cosmos itself. The very act of searching implies a belief, or at least a hope, that we are not solitary beings adrift in an uncaring void. It's the cosmic equivalent of a child looking out a window, hoping to see a friend. The potential discovery of even the simplest microbial life on another world would shatter our anthropocentric view, placing us within a grander biological narrative. It would suggest that the complex chemical dance that led to life here has occurred, or is occurring, elsewhere. This would democratize life, making it a natural outcome of planetary evolution under the right conditions. Imagine the implications. The universe teeming with life, an unimaginably diverse biosphere spread across countless star systems. The implications for our own existence would be staggering. We would no longer be the sole proprietors of consciousness or biology, but rather one expression of a universal biological imperative. This realization could foster a sense of profound connection, a feeling of belonging to a vast, living cosmos. It would redefine our understanding of what it means to be alive, to be conscious, and to be human. The search itself, regardless of its outcome, expands our perspective. It forces us to confront our own limitations and biases, to think beyond the familiar confines of our terrestrial experience. It encourages us to consider the vast range of possibilities that the universe might hold. The sheer audacity of the question, "Are we alone?" is a testament to our own drive to understand our origins and our destiny. It is a recognition that our story, however unique it may seem from our limited vantage point, might be a chapter in a much larger cosmic epic. The quiet hum of a radio telescope pointed towards the inky blackness is a modern prayer, a scientific incantation, a hopeful whisper sent into the cosmic ether, asking, "Is anyone else out there?" This quest is not just about finding aliens. It's about finding ourselves reflected in the vastness, about discovering our true cosmic context, and perhaps finding a sense of belonging in a universe that, at first glance, seems overwhelmingly immense and empty. It is the search for our cosmic neighbors, for the possibility of a shared existence, a universal family tree that stretches across galaxies. It is the profound hope that the spark of life, which we cherish so dearly on Earth, has ignited elsewhere, creating a symphony of existence that we are only just beginning to perceive. This quest is the ultimate expression of our desire to understand our place, not just on this planet, but within the grand, unfolding narrative of the cosmos, a narrative that might be far richer and more populated than we can currently imagine. It is the yearning to know that our existence, our consciousness, our very being, is not an isolated phenomenon, but a part of a universal phenomenon, a vast and interconnected web of life. The search for other life whispers to us that we might not be alone, but rather part of a grand, interconnected cosmic family. The scale of cosmic distances is almost incomprehensible. When we attempt to grasp the sheer immensity of the cosmos, our everyday notions of distance begin to unravel. We measure our lives in meters, our journeys in kilometers, and perhaps our continents in thousands of kilometers. But the universe operates on a scale that dwarfs these familiar units into utter insignificance. Imagine, for a moment, the Earth. It's a rather substantial planet, isn't it? Yet it is merely a speck of dust, a fleeting mote of light, lost within the vastness of our solar system. The distance from the Earth to the Sun, a journey that light itself takes a mere 8 minutes to complete, is approximately 150 million kilometers. To put that into perspective, if you were to travel in a car at a constant speed of 100 kilometers per hour without stopping, it would take you over 170 years to cover that distance. And this seemingly enormous gulf is but a whisper in the grand cosmic narrative. Our Sun, a star of average size and brilliance, is just one of hundreds of billions of stars residing within our own Milky Way galaxy. The diameter of the Milky Way is estimated to be around 100,000 light-years. A light-year, a unit of distance, not time, represents the distance light travels in 1 year. Since light travels at approximately 300,000 kilometers per second in 1 year, it covers an unfathomable distance, roughly 9.5 trillion kilometers. So, 100,000 light-years translates to a number so large it strains the very limits of our imagination, 950 quadrillion kilometers. To traverse our own galaxy from one edge to the other, even at the speed of light, would take 100,000 years. And our galaxy, this colossal structure of stars and gas and dust, is itself just one among an estimated 2 trillion galaxies in the observable universe. These galaxies are not uniformly distributed. They are clustered together, forming vast cosmic webs, separated by immense voids of seemingly empty space. The nearest large galaxy to our own, the Andromeda Galaxy, is about 2.5 million light-years away. This means the light we see from Andromeda today left that galaxy 2.5 million years ago, a time when early humans were just beginning to develop sophisticated stone tools. Even within our galactic neighborhood, distances are staggering. The closest star system to our own, Alpha Centauri, is over 4 light-years away. This means that even if we could travel at the speed of light, a feat currently confined to the realm of science fiction, it would take us over 4 years to reach it. The distances between these stellar islands are so vast that the concept of neighboring takes on a profoundly different meaning. We are not simply separated by a few kilometers. We are separated by gulfs of space so immense that they can only be measured in units that reflect the speed of light itself. The largest structures we observe, like the Sloan Great Wall or the Hercules Corona Borealis Great Wall, are galaxy filaments stretching for billions of light-years. These are not mere collections of galaxies. They are cosmic superhighways, vast rivers of matter and energy that dwarf entire galaxies into microscopic points. Our understanding of these distances is not static. It is a constantly evolving picture pieced together by the tireless efforts of astronomers and cosmologists. Using sophisticated telescopes and ingenious methods of measurement, such as parallax, standard candles like Cepheid variable stars, and the redshift of distant galaxies, we gradually map out this immense tapestry. Each new discovery pushes the boundaries of what we thought we knew, revealing yet more profound depths to the universe's scale. The very act of comprehending these distances requires a fundamental shift in our perspective, a willingness to shed our terrestrial biases and embrace a cosmic viewpoint. It is a humbling realization that our planet, our star, and even our galaxy are but infinitesimal components within this grand, almost unimaginable cosmic architecture. The sheer scale of it all serves as a potent reminder of our place, not as the center of everything, but as a tiny, precious part of an immense and wondrous whole. These cosmic distances are not just numbers. They are testaments to the boundless potential and staggering beauty of existence, reminding us that our everyday concerns are but a fleeting moment in an eternity of space. Light travel time gives us a glimpse into the past. Imagine standing on a shore, watching a distant ship. The waves you see have traveled across the water, carrying with them the history of their journey. In a similar, yet profoundly more expansive way, the light that reaches our eyes from celestial objects is a messenger from the past. When we gaze at the stars, we are not merely observing them as they are now asterisk, but as they were at the moment the light departed their surface or their vicinity. This is not a metaphor. It is a fundamental consequence of the finite speed of light. The universe, in its vastness, acts as an immense time machine, powered by the very photons that illuminate our world. Consider our sun. It is approximately 150 million kilometers, or about 93 million miles, away from Earth. Light travels at an astonishing speed, roughly 299,792 kilometers per second, or about 186,282 miles per second. Even at this incredible velocity, it takes sunlight about 8 minutes and 20 seconds to traverse the immense gulf between the sun and our planet. This means that when you look at the sun, you are seeing it as it was over 8 minutes ago. If, hypothetically, the sun were to suddenly vanish, we would not know about it for over 8 minutes. This delay, though small in our daily experience, is a constant reminder of the vast distances involved in astronomical observation. As we extend our gaze further into the cosmos, the temporal lag becomes dramatically more pronounced. The Alpha Centauri star system, our closest stellar neighbor, is about 4.37 light-years away. A light-year is the distance light travels in 1 year, a distance of approximately 9.46 trillion kilometers, or 5.88 trillion miles. Therefore, the light we receive from Alpha Centauri tonight left that star system 4.37 years ago. We are seeing Alpha Centauri not as it is now, but as it was nearly 4.5 years in the past. This principle applies to every star we see in the night sky. The twinkling lights are not instantaneous snapshots of the present, but rather echoes of light that has journeyed for years, decades, centuries, and even millennia to reach us. When we observe distant galaxies, the concept of looking into the past becomes even more profound. The Andromeda Galaxy, the nearest major galaxy to our own Milky Way, is approximately 2.5 million light-years away. This means that the light we are collecting from Andromeda tonight began its journey when early hominids were beginning to walk the Earth. We are, in essence, looking back 2.5 million years into the history of another galaxy. Some of the faintest and most distant galaxies we can detect with powerful telescopes, like the Hubble Space Telescope or the James Webb Space Telescope, are billions of light-years away. The light from these galaxies has been traveling for a significant fraction of the age of the universe itself. When we observe these ancient beacons, we are witnessing the universe in its infancy, a time when the first stars and galaxies were just beginning to form. This ability to peer into the deep past is one of the most extraordinary consequences of the finite speed of light, allowing us to reconstruct the cosmic timeline and understand the evolution of the universe. It transforms every astronomical observation into a journey through time, revealing the universe not as a static panorama, but as a dynamic, evolving entity whose past is forever etched in the light that reaches us. Thus, every photon is a time traveler, carrying with it not just illumination, but the very history of its origin. The observable universe is just a fraction of the whole. Imagine, for a moment, the vast expanse we can perceive, the cosmic tapestry woven with light from distant stars and galaxies, the entirety of what our most powerful telescopes can reveal. This observable universe, this immense sphere of existence that we can, in principle, detect, is a breathtaking testament to the grandeur of reality. It stretches across an unfathomable distance, approximately 93 billion light-years in diameter, a sphere so vast that our minds can barely grasp its scale. Within this boundary, we find countless galaxies, each a swirling metropolis of billions of stars, nebulae painting the void with ethereal colors, and the faint whispers of ancient light that have traveled for eons to reach us. It is a realm of unimaginable beauty and complexity, a cosmic ocean in which our own planet, our own sun, our own galaxy are but infinitesimal specks. We can map its large-scale structures, observe the cosmic microwave background radiation, the afterglow of the Big Bang, and study the distribution of matter and energy across these immense scales. We can trace the history of the universe, from its fiery beginnings to its present, ever-expanding state. The light that reaches us from the most distant observable galaxies began its journey when the universe was a mere fraction of its current age, offering us snapshots of cosmic epochs long past. This observable sphere represents everything that has had enough time for its light to reach us since the Big Bang. It is, in essence, the limit of our cosmic horizon, defined by the finite speed of light and the finite age of the universe. Every star, every galaxy, every phenomenon we can ever hope to detect lies within this cosmic bubble. It is the totality of our empirical knowledge of the cosmos, the grand stage upon which all known cosmic events have unfolded and are unfolding. The sheer volume of this observable realm is enough to inspire profound awe, to make us contemplate our place in the grand scheme of things. We see structures that dwarf our understanding, phenomena that defy our everyday experience, and a history that stretches back to the very dawn of time. Yet, this immense sphere, this limit of our perception, is not the entirety of existence. It is merely the part of the universe that is accessible to us, the portion whose light has had time to traverse the cosmic distances and arrive at our telescopes. The universe itself is believed to be far, far larger than what we can observe, potentially infinite. Our observable universe is like a small island in an immeasurably vast ocean, or a single illuminated room in an infinite, dark mansion. The edge of our observable universe is not a physical boundary in space, but rather a temporal and causal one. It is the farthest point from which light has had time to travel to us since the universe began. Beyond this horizon, there may be more galaxies, more cosmic structures, more wonders that we can currently only speculate about. The expansion of the universe complicates this picture further. As space itself expands, regions that were once within our observable horizon can recede beyond it, and new regions that were previously beyond reach can, in a sense, become observable as light from them eventually catches up. The observable universe is a dynamic entity, its boundaries shifting with time and the ongoing expansion of space. This concept is both humbling and exhilarating. It suggests that the grand cosmic narrative we are piecing together, while vast and awe-inspiring, is but a chapter, a glimpse into a story that is infinitely larger and more complex than we can currently comprehend. It fuels our curiosity, driving us to push the boundaries of our knowledge and technology, to seek out new ways to perceive and understand the universe. The fact that our observable universe is a fraction of a whole implies that there are realms of existence, scales of reality, and cosmic phenomena that lie entirely beyond our current grasp, waiting to be discovered, or perhaps forever remaining mysteries. This profound realization is a cornerstone of cosmic humility, reminding us that our current understanding, however advanced, is inherently limited. It is a call to perpetual exploration, a testament to the boundless nature of reality itself. The edge of our cosmic vision is not the edge of existence, but merely the limit of our current reach, a gentle reminder of the vastness that lies just beyond our sight. The universe may be infinitely large, or it may be finite. Imagine, for a moment, standing at the very edge of what we can perceive, the furthest reach of our observable cosmos, and then contemplating what lies beyond. This is where our current scientific understanding meets a profound philosophical question, a contemplation of scale that touches upon the very nature of existence itself. The question of whether the universe is finite or infinite is not merely an academic exercise. It delves into the fundamental geometry and topology of space-time. For centuries, philosophers and astronomers have pondered this. If it is finite, does it have an edge? And if it has an edge, what lies beyond that edge? These are questions that push the boundaries of our intuition, which is so deeply rooted in our everyday experiences of enclosed spaces and bounded objects. Our minds are accustomed to thinking in terms of containers, of things that begin and end. But the universe, in its grandest scope, may defy such simple categorization. Consider, first, the possibility of a finite universe. This doesn't necessarily mean a universe with a hard boundary like a wall. Instead, it could be finite in volume but unbounded, much like the surface of a sphere. If you were to travel in a straight line on the surface of a sphere, you would eventually return to your starting point without ever encountering an edge. Similarly, a finite, unbounded universe could curve back upon itself. If you were to travel far enough in one direction, you might, in theory, find yourself back where you began. This concept, known as positive curvature, suggests a universe that is closed. The total amount of matter and energy within such a universe would dictate its curvature. If the density of matter and energy exceeds a critical value, the universe would be positively curved and finite. However, observations made by missions like the Planck satellite, which studied the cosmic microwave background radiation, suggest that the universe is remarkably flat, or very close to flat. A flat universe, in the simplest geometrical model, would be infinite. Now let us explore the implications of an infinite universe. In this scenario, space-time stretches out forever in all directions, containing an unending procession of galaxies, stars, and planets. This concept is perhaps even more challenging to grasp. If the universe is infinite, then any arrangement of matter that is possible, however improbable, must exist somewhere within it, an infinite number of times. This leads to mind-boggling possibilities, such as infinite copies of ourselves living out identical lives, or variations of our lives, in distant, unreachable regions of this boundless cosmos. The flatness observed in the cosmic microwave background strongly supports the idea of a geometrically flat universe, which, according to standard cosmological models, implies an infinite extent. However, our observations are limited to the observable universe, the portion of spacetime from which light has had time to reach us since the Big Bang. We cannot definitively say what lies beyond this horizon. It is possible that the universe is finite but so vast that its curvature is imperceptible within our observable region, making it appear flat to us. Alternatively, it could be truly infinite. The distinction between an extremely large, finite universe and an infinite one can be practically indistinguishable for us. The very question challenges our limited human perspective, forcing us to confront the possibility that reality extends far beyond our comprehension, in ways that are both awesome and humbling. The universe's ultimate size remains one of its most profound mysteries, a testament to the vastness that lies just beyond our current grasp. The universe's ultimate size, whether a boundless expanse or a cosmic sphere, whispers of a reality so grand that it dwarfs our every concern, reminding us of our place within an immensity that is both incomprehensible and infinitely inspiring. Our understanding of the universe is constantly evolving. The cosmos, in its unfathomable immensity and intricate detail, remains a frontier of perpetual discovery, a grand tapestry woven with threads of the known and the yet-to-be known. For millennia, humanity has gazed upwards, seeking to decipher the celestial dance, to comprehend our place within this vast expanse. Early astronomers, with meticulous observation and nascent mathematical tools, charted the predictable movements of the stars and planets, laying the groundwork for what would become a profound scientific endeavor. Their models, though eventually superseded, were crucial steps, representing the very best of human intellect applied to the mysteries of the night sky. Think of the ancient Greeks, with their geocentric models, or Copernicus and Galileo, who bravely shifted our perspective to a heliocentric view, a revolution in thought that challenged deeply ingrained beliefs and opened up new avenues of inquiry. This journey of understanding has never been a straight line. It has been a series of breakthroughs, of paradigm shifts, where old certainties are questioned and new, more comprehensive explanations emerge. The advent of the telescope, for instance, unveiled a universe far richer and more complex than previously imagined, revealing nebulae, distant galaxies, and the moons of Jupiter, each discovery a testament to the power of observation and the relentless human drive to see further. Then came the laws of motion and gravity, articulated by Newton, which provided a unifying framework, explaining the celestial mechanics with elegant simplicity. This was a monumental achievement, but even Newton's laws, while incredibly successful, hinted at deeper complexities, particularly when applied to the very fast or the very small. The 20th century, in particular, witnessed an explosion of new ideas that fundamentally reshaped our cosmic perspective. Einstein's theories of relativity, both special and general, introduced concepts like spacetime, the curvature of gravity, and the interconnectedness of mass and energy, pushing the boundaries of our comprehension. Suddenly, the universe wasn't just a static stage for predictable events. It was a dynamic, malleable entity, where space and time themselves could be warped and influenced. The discovery of the expanding universe, through the redshift of distant galaxies, revealed that our cosmos is not a fixed entity, but is in a state of continuous change, a revelation that sparked entirely new questions about its origin and ultimate fate. The development of quantum mechanics further deepened this enigma, unveiling a realm of reality at the subatomic level that defies classical intuition. Particles can exist in multiple states simultaneously. their behavior governed by probabilities rather than certainties, a paradox that continues to challenge our understanding of fundamental reality. Even concepts that seemed settled, like the age and composition of the universe, are subject to refinement as new data emerges from increasingly sophisticated instruments like the Hubble Space Telescope and the James Webb Space Telescope. These powerful observatories allow us to peer further back in time and with greater clarity than ever before, revealing the first galaxies, the birth of stars, and the intricate processes that shape cosmic structures. The ongoing exploration of dark matter and dark energy, which constitute the vast majority of the universe's mass-energy content, highlights how much we still have to learn. These enigmatic components are inferred from their gravitational effects, yet their true nature remains one of the most significant puzzles in modern cosmology. The very act of scientific inquiry, with its emphasis on hypothesis, experimentation, and peer review, ensures that our understanding is not static, but is a living, breathing process. New observations can challenge existing theories, leading to revisions, refinements, or even complete overhauls of our cosmic models. It is this constant evolution, this relentless pursuit of knowledge, that makes the study of the universe so endlessly fascinating. We are not merely passive observers. We are active participants in this grand unfolding, our questions and discoveries shaping the very narrative of cosmic comprehension. The universe is not a closed book. It is an ever-expanding library, and we are only just beginning to read its most profound chapters. Each page turned revealing more questions, more wonders, and a deeper appreciation for the magnificent mystery that surrounds us. In this grand, unfolding narrative of cosmic discovery, our knowledge is a river, ever-flowing, ever-changing, a testament to the enduring human spirit of inquiry that finds its deepest peace in the pursuit of truth. The true scale of the universe inspires humility and wonder. Consider for a moment the sheer immensity we have explored, from the subatomic dance of quarks to the majestic sweep of galactic clusters. We have journeyed through the fundamental forces that bind reality, the energetic vacuum that hums with potential, and the unseen architecture of dark matter and dark energy that sculpts the cosmos. We have witnessed the fiery birth and dramatic death of stars, the enigmatic embrace of black holes, and the vastness of our own galaxy, the Milky Way, a mere speck within a cosmic ocean. We have contemplated the possibility of other worlds, other suns, and the profound implications of whether we are alone in this grand expanse. Each step of our exploration, each revelation, has served to underscore a singular, profound truth. The universe is, in its truest sense, immeasurable by our everyday standards. Our human perception, honed by the relatively small scales of our terrestrial existence, struggles to truly grasp the distances that separate celestial bodies, the timescales over which cosmic events unfold, and the sheer number of stars, planets, and galaxies that populate the observable universe, let alone what lies beyond. This struggle to comprehend is not a failing, but rather a testament to the extraordinary nature of reality itself. It is a natural human response to confront something so overwhelmingly vast, so profoundly intricate, that it dwarfs our individual significance. Yet, within this very dwarfing lies a remarkable freedom. When we truly internalize the scale of the universe, our personal worries, our anxieties, and our immediate stresses can begin to recede. They do not disappear, but their relative weight diminishes. The problems that consume our daily lives, while real and important to us, are placed into a much grander context. The universe does not care about our deadlines, our disagreements, or our fleeting concerns. It simply is asterisk, an ongoing, magnificent unfolding of physical laws and cosmic phenomena. This perspective is not meant to be dismissive of human experience, but rather to offer solace. It suggests that our existence, however brief and small on a cosmic scale, is part of something infinitely larger and more enduring. The very fact that we, as conscious beings, can even contemplate this scale, can develop the tools to measure it, and can experience a sense of awe at its grandeur, is itself a marvel. It speaks to our own deep connection to the universe, a connection forged in the stardust of ancient stars. The humility that arises from understanding our place in this vastness is not a surrender, but an elevation. It is the humility of recognizing our interconnectedness with all things, the quiet understanding that we are not isolated entities, but integral components of a magnificent, ongoing cosmic narrative. This perspective can be a powerful antidote to the anxieties that keep us awake, a gentle reminder that we are part of something far greater than our immediate circumstances. The wonder that such scale inspires is a profound source of peace. It is the wonder of the unknown, the beauty of the complex, and the deep, quiet satisfaction of learning and understanding. It is the feeling of standing on the edge of an infinite ocean, aware of its boundless depth and power, and finding not fear, but a profound sense of calm and belonging. This contemplation of cosmic scale invites a surrender to something larger than ourselves, a release from the confines of our own limited viewpoints. It is in this surrender, this acceptance of our small yet significant place, that true peace can begin to settle. The universe, in its overwhelming vastness, offers not a burden, but a balm, a gentle whisper that our worries are but fleeting ripples on an infinite, majestic sea. In the quiet contemplation of the universe's immeasurable expanse, we find a profound sense of our own smallness. Yet within that smallness, a boundless wonder is born, reminding us that even the tiniest spark of awareness is part of an infinite, awe-inspiring dance. Our calm exploration has covered the astonishing scale of the universe, from the infinitesimal realm of quarks and quantum fields to the majestic, sprawling architecture of galaxies and the accelerating expansion of spacetime itself. We have journeyed through the unseen forces that shape reality, the energetic dance of stars, and the profound mysteries of dark matter and dark energy. Tonight, we have reviewed the principles that govern everything from the smallest vibration to the grandest cosmic structures, reminding us that even in the most minuscule or the most immense, there is a profound, interconnected order. Consider this vastness, this intricate tapestry of existence. The very atoms that compose you were forged in the heart of stars, connecting you directly to the cosmic furnace. The space between these atoms, so seemingly empty, is a vibrant, energetic sea governed by laws that stretch across unimaginable distances. This perspective, this gentle understanding of our place within such immensity, can be a profound balm for a restless mind. It whispers that our worries, while real, are but fleeting moments in the grand, unfolding narrative of the cosmos. You are a part of this extraordinary, ongoing creation, a conscious observer of its wonders. It is time to rest now. Allow the immensity of it all to wash over you, to dissolve the sharp edges of the day, and to cradle you in a sense of peaceful belonging. Sleep well. Good night. If you happen to still be awake, you can drift into the next chapter now, continuing our quiet exploration of the universe's boundless secrets.